Assalamu alaikum. Bismillahirrahmanirrahim. Rabbi sadri wa yassir li wahlul 'uqdatam min lisani yafqahu qawli. In the last lecture of 7, we have completed the definition of phase of a pure substance. We called pure substance as a uniform and invariable substance in a chemical composition that is not changing with the by increasing temperature or by shifting any substance from one phase to another, like from solid to liquid and liquid to vapor. There will be no change in chemical composition. That is called to be pure substance in thermodynamics. And we know that there we have three states: solid, liquid and vapor. So move on the next slides. We also completed this slide that when we heat the water at certain pressure, that pressure is not increasing, it is atmospheric pressure. So water will keep increasing its temperature until 100 degrees centigrade, and after 100 degrees centigrade it will not after still heating after 100 degrees centigrade, that will not increase the temperature of water. So by plotting these values in the temperature versus volume graph, we see that the volume will increase. In the last class I told you that this piston moves from state 1 to from state 2 by increasing its volume, that is delta V. That is a change of volume from going from 20 degree to 100 degrees centigrade by keeping the pressure constant at certain at one atmospheric pressure, that is. So when we plot this graph, the point is moving like this, the temperature is increasing and as well as volume is increasing. After reaching this point, what will happen? Once boiling start, temperature stop rising until the liquid is completely vaporized. After that, the temperature is by giving more heat, more temperature to the vessel or any boiling pan like this, it will not increase the temperature but producing gases. This is gases until the whole water converts into the gas. In this case we have some liquid and some gas, but after vaporizing whole water into steam, we have a single phase of a systems in this cylinder. During a boiling process, increase the volume and steadily decline in the liquid levels. At midway of vaporization, cylinder contains equal amount of liquid and vapor. Of course, in the midway we have half liquid, half gas, continuing transferring heat until the last drop is vaporized. At this point, the entire cylinder is filled with vapor known as saturated vapor. So in the last class we term liquid as a subcooled liquid or compressed liquid. These are the two terminologies used for the liquid state in thermodynamics: compressed liquid or subcooled liquid. Because in the middle stage like this, it is a partial liquid, is a partial vapor, so we call them saturated vapor. And in the later diagram I will show why we do not use only liquid for the complete liquid form. We use compressed liquid or subcooled liquid. You will understand in the later this slide. I think so. Yes. So by plotting this phase change process in temperature versus volume graph, this is 0.2 and this is 0.3 and so on. So when we heating after 100 degrees centigrade, the water will vaporize, and in this process the volume is steadily increased as written in the previous lines. The volume is increased but temperature is not increased until the whole water converts into steam, and it is called saturated vapor. Here in this point we call that saturated vapor, and in this point we call them a saturated liquid. That's why in this portion we do not only call liquid, we used to put compressed liquid or subcooled liquid, because we have to differentiate this point and this point. So in this point we have before liquid there's a saturated liquid. Now I hope you understand this phase change process from liquid to vapor. Once the phase change process is completed, we are back to single phase region again. In this portion, it is a single phase compressed liquid. It is a mixture of liquid and vapor, and at this point the whole liquid convert into the gas or saturated vapor. So again we comes into the single phase region. Further transfer heat result in increase in the both temperature and specific volume. At the state 5, temperature of the vapor is, let's say, 300 degrees centigrade. Heat transfer from the vapor, temperature decreases but no condensation take place. A vapor that is not about to condense, not saturated vapor, is called superheated vapor. Like for after this point, after goes into the single phase of water in the form of a steam. If it is the water, then it is a steam. In normal nomenclature, the name for the gas of the water is steam. So we reach that steam or saturated vapor in thermodynamics terminology, and in general terminology it is a simple gas. So after heating this point, then the phase is completely changed. So again temperature will rise like this, and specific volume also rise. So specific volume also rise, temperature is also rising, and in this state we can call this vapor not only in this position we are calling this a saturated vapor, but after that point we call them a superheated vapor. Superheated vapor. So now at a given pressure, temperature at which a pure substance change phase called is saturation temperature, and position where the at a given pressure the temperature at which pure substance changes its phase is called saturation temperature. We call them boiling state 2. Likewise, at a given temperature the pressure at which pure substance changes called saturation pressure. Let us add weight on the top of the piston until the pressure inside the cylinder reaches 1 megapascal. Now heat is transferred to the water. Boils at higher temperature. Specific volume of saturated liquid is larger and specific volume of saturated vapor is smaller than 1 atm. As the pressure increases further, the saturation line continues to shrink. So in this case, this is a graph of 1 atm. In the whole process, the pressure, we kept the pressure constant to 1 atm. Now for an example, if we put some weight on the cylinder, this cylinder, then we cannot make the pressure of 1 atm, but it will increase pressure because it having a weight. So how much weight we are putting to reach it 1 megapascal. Now what will happen? It is showing in this graph. So this is a graph of 1 megapascal. Okay. So now in this case, this is graph of so this is a graph of, this is a scale of 1 atmosphere, because 1 atm is 110 to the power 5 pascal. So when converting into the megapascal, mega means 10 power 6, so it is 0.1 megapascal. 1 atm is 0.1 megapascal. So this is the graph of previous graph, but if we increase the pressure like 1 megapascal, the boiling point boiling point of that water will increase, and as well as the specific volume will increase. Like in this case, the specific volume at the saturation point, this is called saturation point. So in this case, the specific volume will also increase, and as well as the temperature when the water is boiled, or whatever the system is start its phase changing process. So in the similar way, if we keep increasing the pressure in the piston, we are getting higher temperature and higher specific volume, and the phase change process shrinking as told in this point. As the pressure increase further, the saturation line continues to shrink. So you can notice that by increasing the temperature, the phase change process now getting shrink, like until it reaches this point. This is called critical point, and after that point we call them supercritical region. So these are the regions of, if we point out these point, these region of liquid is subcooled or subcooled liquid or compressed liquid. These region, if you draw this like this, we make line this, so we make the region. This region is subcooled liquid or compressed liquid. This is a saturation region, like the mixture, saturated vapor, liquid, and this point, this line is saturated vapor, this point is saturated liquid, and after this region, this is the superheated region. So we have three different region: saturated region, superheated region, and subcooled liquid. By joining this point, we make a line that is called wet dome. In thermodynamics, it is called wet dome. Anything which is left to it is a complete compressed liquid or liquid region. Anything which is under this line, it is called saturated liquid vapor region. It's a mixture, and after that we have a superheated region. And at this point, every properties is saturated liquid. At this point, every properties are saturated vapor properties, and we call this line as saturated vapor line, and we call this line as a saturated liquid line. And this is the center of the point, where you can see that there is no phase change process. Water will heat and then directly goes into the gaseous region. So there is no mixture of liquid vapor. So that is a critical point, we call a 3 point or critical point. And after this region, if we increase pressure more than this is like in the previous diagram, this is 0.1 megapascal, 0.01, 0.1, 8, 15, 22, and after 22, this is the basically pressure points of water. If we use another substance, the pressure value something else, in whether it is increase or decrease. So right now we are talking about water. So for water act like this. After reaching 22 megapascals, it's a very high pressure. So after reaching that point, critical point, the substance we call them a supercritical region. It is a supercritical region. And I would like to tell you that in the practical world, these machinery are still exist, like 2.22 mega like in HUBCO, they recently installed 22 megawatt power generation system from the coal, and the boiler in this power generation system is used supercritical boilers. Some of my students get the job in the HUBCO power plant, new HUBCO power plant installed at the hub river, and it is based on supercritical boilers. The boiler are working on supercritical region. They are boiling the water more than they are boiling the water more than 22 megapascal of pressure. So we have advantage over it. It's a detailed topic, and for the mechanical people, I would we will tell the how we are making that much high pressure and what are the benefit of it. There are benefit of it. Even you can understand that by increasing the pressure, the phase change process shrinking, so we are minimizing the process timing. Also we are minimizing um, the vapor region which can form fog in later process of turbine, which can hit the liquid, the the vapor in the steam hit the blade and it erode the blade, so it is dangerous. So we are minimizing the risk as well as the time, and we are also increasing the efficiencies after going to the supercritical region. But of course it costs money. The fabrication system, the overall equipment cost becomes higher in running at that much higher pressure, because at higher pressure we have to put some extra material to hold that pressure, and it's also very high critical jobs. If anyone due to any negligence, that pressure can abrupt the whole area and there's a blast in that particular area. So it's a very critical job, and we have very trained people over there. So this is the example of how we are using this water in any power generation sector. We are convert this water into steam, and then steam will run the turbine. In later we will I will add some animation to it. So now we have studied this temperature versus volume graph. So we are also understand the regions. Now we are now we are getting properties at these particular regions. How we acquire these regions and utilize in the numerical. In the next slide told us about that. One of the most important property in thermodynamics is enthalpy. It is a simple property. It is not by physical means. It is a combination. It is a combination of properties in thermodynamics. Thermodynamics frequently encounter the combination of properties like internal energy and pressure volume work, PV. The equation for the work is integral P dV. It is a more accurate equation, but in the short form we can write P del V. So it is a work, it is an internal energy. So by combining these two properties, internal energy and pressure volume work, there are some other work in thermodynamics, but the pressure volume work and internal energy combines to form enthalpy. For most systems, the relation among the thermodynamics properties are too complex to be expressed by simple equations. Therefore, properties are frequently presented in the form of tables. So these are there are a lot of properties. So we form a table, and later slide we will see that how the table help in getting the actual values of the pure substance, and how we are calculating energy and how we are calculating power, etc. So right now you understand what is enthalpy. It is simple. It is a simple combination of two properties, internal plus pressure volume work. Means that in the physical point, I will make you understand that let's suppose at steam is at this point, saturated vapor. Now this saturated vapor can do work, and it also have energy, internal energy. For an example, if we have a cylinder like this, if we hold this cylinder, then all the energy is in the internal energy, but it is doing, if we reduce the weight or utilize this internal energy into work, the piston moves upward, and this saturated vapor is going to do some work. Even if it is doing work, it has some internal energy. So combining these two, internal energy plus work, we used to call the special properties enthalpy. It is a capability of steam to do work and have internal energy. Okay, every system have in practical work all the energy cannot be converted into the work. So it is basically a capacity. It is basically a capacity how we are using the energy of steam into work, and how the internal energy can be converted into the work. So it is we used to counter the combination of these two properties. Anyway, the formula is so simple. Capital H is enthalpy, U is internal energy, P delta V is pressure, volume, work. But if we divide with all the properties with mass, now it becomes specific. All the properties becomes now specific. As we learned in the previous lecture, anything divided with the mass, it becomes a specific, like a specific volume, specific internal energy. In the same way, the capital H becomes a smaller h, and now it is specific enthalpy. It is a specific internal energy and a specific volume, small v. So the overall unit of this equation will, of course, kg per kilojoules per kilogram. And if we denote these properties with respect to this region, so we make the table. Later we will show how we are using the table. So any properties lies in this point are subscript with F. The subscript F is used to denote the properties of saturated liquid. So any properties like internal energy, enthalpy, specific volume, subscripts with F are called to be saturated liquid lines. Any properties in this region are called to be separate, and we have a graph of this saturated liquid vapor region separately, this compressed liquid region separately, and superheated region graph separately. So any properties in this region are used to denote by simple U, H and V, specific. And even in this we have U, H, V. We know that it is a uniform region, so we don't need to subscript with anything else. Anything which is internal energy. But in this region we have three different modes of every properties. Like in this point we have a saturated liquid point, like in the middle we have a half liquid and half vapor. So we used to subscript with U, F, G. Or even in this case we used to denote the quality. Later we study how we are denoting the quality, but we in this between region we used to subscript F and G both. And at this point we used to subscript with UG, HG and specific volume with G. So at this point every property is subscript with G, at this point with F, and in the middle of these two regions we subscript with combination of FG. So this is written over here. The subscript F is used to denote the properties of saturated liquid. The subscript of G denote the property of saturated vapor. The subscript Fg which denote the difference between the saturated vapor and saturated liquid values of same property. So I hope you understand these properties. Now we are going towards the table. How we are studying the table and how we are calculating the table, that we will use here. This is thermodynamic table of an SI unit. I shared in the books and reference folder. You can download its copy by your own end. So these are the different table. Now move toward this, that the table A4 represent saturated vapor temperature table. The table A5 represent saturated vapor pressure table. In thermodynamics we have two types of different table in saturated region especially. One is along the temperature and one is along the pressure. So we have a temperature values like 100, 101, 102 or like 100, 110, 120. in a specific manner and along its pressure like 2 pascal, 2.2 kilopascal, and when it is called when it is around pressure, we have a 0.1 pascal, 2 pascal, and along with the temperature 101, 102, and so on. So A6 is superheated vapor, A7 is compressed liquid water table, and after we have saturated ice vapor, etc. So let's move on towards A4. This is ideal gas equation table. So this is saturated vapor, like the properties in wet dome. So we have two different, in the specific volume we have Vf for saturated liquid, Vg saturated vapor. For internal energy we have both three properties, like saturated liquid Uf, in between Ufg, and saturated vapor Ug. And enthalpy, of course, we also have three properties. In entropy, later we study entropy, we also have these properties. So you will now you have a question that the value is fixed, Ufg is fixed. Now where it is lie, in the start, in the middle, or in the, like in this table, you get answer that Uf value is lie for a particular pressure, like for 1 atm, like this graph. If we call Uf, the property lie here. If we call Ug, the properties of this point. But what about Ufg, where it is lie in this portion, here, 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 here. So now to calculate the properties in between region, we have another parameter that is called x, and x to be called to be efficiency. Efficiency or quality, sorry, not efficiency but the quality. X shows the quality of steam. If it is like this, we used to have quality 1, maximum quality. If have quality 0, it is lie here, 0 quality, 0 steam. And if in the middle we have a x is equal to 0.5. If we call them in a percentage, it is 100%, it is 50%. Means that in this region the value of x is 0, in this region the value of x is 1, that is 100% steam. In the middle we have a value of 0.5, and in this particular region we might have value like 0.1, 0.2, 0.3, 0.4, 0.5, 6, 7, 8, 9, and then 1. And how we are calculating the in between properties? It is simply let's remove extra thing. Now how we are calculating? By simple equation. Let's suppose if we calculate in enthalpy of, sorry, we have to select pen. If we need to need to calculate the property here, let's suppose we have the quality of steam is 0.6 over there. We can calculate by a different experimental tool. Okay, so let's we have a quality of steam is 0.6. Now we have to calculate the property like enthalpy. So we have an equation to calculate the property in this is HF plus quality of steam multiplied by HFG. HF plus X HFG. Let's suppose we need to calculate the enthalpy of the system at 50 degree centigrade. and 12.5 kilopascal. It is a saturation at 50 degrees centigrade. The saturation pressure will be 12.53. At this point, water boil, means that you can see that at 1 atm, that is 101.42 kilopascal, it is 1 atm. The boiling point is 100 degrees centigrade. But if we decrease the saturation pressure, the boiling point will also decrease, and if we increase the pressure, the boiling point will also increase. So this is basically a saturation pressure. For an example, if we have a, okay, let's take 1 atmospheric pressure. Let's we have a 1 atmospheric pressure. The boiling point or saturation temperature is 100 degrees centigrade. We have to calculate the enthalpy at a quality of 0.6. So we take the two different value, that is HF across the 100 degrees centigrade. How this is how we are studying the graph. We take HF and as well as HFG. Now we put these two values here. What is HF? HF is 419 and 2256. 419 plus 0.6 multiplied by 2256. Now multiply by this, adding this, we get the answer of enthalpy at quality of 0.6. So this is how we are calculating the in between values, and for this point we don't need to calculate or apply equation. We directly get the values of this point from steam table, and even from this we also get the values from steam table. But what about at this point? If we need to calculate the value of properties here, we have another graph, that is A7, or let's see what is the type, what is the number of this graph. We have to see the table over here and we get the answer. And if we need to calculate the values here, we just simply need to know the pressure, that this pressure, or this pressure, we get the values. And in compressed liquid, we only need to know the pressure and temperature, we get the values. Let's see how. This is steam tables. This is steam table with respect to temperature. You can see the variation of temperature in the specific manner, like 5, 10, 15, 20, so on. So this table can also convert into the pressure standard. It is a temperature standard. Temperature values are in the standard manner, but the pressure are not in the standard manner, because every temperature had different saturation pressure. So the next table like this. Now in this, it is the same table, saturated liquid vapor table, but in this case the pressure are in the specific manner, and temperature values are differ with that temperature. So if we need to calculate, we have a pressure known like 100 kilopascal, we can use this graph. But if we know the temperature, like but in this case temperature cannot be directly linked. But if we know the temperature like 90 degrees centigrade, so we need to see the graph of this 90. Okay, in the pressure table, you won't get actual values, because we have a variation like 81 and 91, not exactly 90. So this is how the table are formed. Now I've told you, if we need to calculate the properties in superheated region or in compressed liquid, we have to shift the table from A4 to A5 to A6. Now table A6 shows the properties of superheated region. In this case, we need to know the temperature and pressure. How? We need to we should have to know the known point are pressure. Like in this case, we have pressure 0.05 megapascal. Now we also know we also need to have temperature. Let's suppose at 0.05 megapascal and 150 degrees C. The specific volume is 3.8, internal energy 25, enthalpy 2780, and entropy 7.94. So by these two properties we get other properties as well as. And if we talk about compressed liquid graph, this is compressed liquid graph. So in the compressed liquid graph, again we need to have pressure values and temperature value to get the values of other properties like specific volume, enthalpy, and internal energy. So I hope you well understand the idea how we are calculating or how we are getting properties of steam or phase properties at different points and different regions. And also we have studied one more properties, that is enthalpy, that is a combination of internal and pressure volume work. So now we have a small numerical over here, very small numerical related to it. It is example 3.1 from the Sengil. These I put this point in the slide, but in the lecture I'll show from actual tables. For an example, I've just placed some snap of steam table over here. So let's move on. Example 3.1. A rigid tank contains 50 kg of saturated liquid water at 90. So by simple word saturated liquid, you get the idea it is in the left line, not in the left point or right point in the center, but it's exact at the this wet dome line. The saturated liquid should be in this point at 90. If the table is temperature volume, so this is 90 degree, and we are talking about this properties at this point. Determine the pressure in the tank and the volume of the tank. So determining the pressure is very easy. We have 90 degrees centigrade, so we move towards that steam table graph which is along the temperature variation. The temperature are in the standard way, so we move toward the graph A4 and we down towards the 90 degrees centigrade. At 90 degrees centigrade, the saturated pressure, like if we in the physical term, this pressure, this table is showing that if we need to boil the water at 90 degrees centigrade, then how much the atmospheric pressure of the water should be. So it is 70.13 kilopascal. Like for an example, in the hilly areas or in the high mountains, we know that the atmospheric pressure is lower, and we already discussed in the lecture number 3 and 4, and have a very good animation videos how by increasing the altitude in the atmosphere, the atmospheric pressure is getting lower because of the weight of the air. We know that. So when we are moving towards high altitude region, we have a problem in cooking, especially because meal will not cook properly. So we need to have a pressure cooker to cook the food, because the water boils at 100 below 100 degrees centigrade, so the cooking is not performing with their standards. So we need to put some extra pressure by pressure cooker, and by this way the temperature of liquid is more than 80, 90, 100. So we cook things very quickly. Even in the at sea level we used to have a pressure cooker. Why we use pressure cooker? To increase the temperature of water more than 100. So in this way, by atmospheric pressure we can increase that boiling point, increase or reduce by differentiating of atmospheric pressure. So in this particular example we get the answer at 90 degrees centigrade. If we boil the water at 90 degrees centigrade, the atmospheric pressure should be 70.13 kilopascal, and atmospheric pressure is 101 kilopascal. So it is almost 30 kilopascal less than atmospheric pressure. Now the second quantity determine the pressure, determine the volume in the tank. So we need to from this graph we can also calculate the volume. How? We know that this is we are talking about this point. So at this point the subscript F shows the specific volume. So what is specific volume here? 0.001036, and we know that the capital volume, the actual volume, is basically what? Mass time specific volume. Like for a specific volume example, we know that it is simply volume divided by mass. So for calculating actual volume, we need to multiply mass with specific volume, and we know that mass 50 kg. So simply 50 multiplied by point this, we get the answer. And what is the answer? Let's multiply. 0.001036 multiplied by 50, it is 0.0518. 0.0518 meter cube. It is simply 50 multiplied by 0.001036, and we get answer over here. So let's stick to it. In the next lecture we will do one more practical numerical. Also we also have an animation of power generation system, how we are utilizing steam in the power generation sector. Till then, Khuda Hafiz, Allah Hafiz, take care.